Greetings and welcome back. I was under the impression that possibly I was not clear on how to formulate the null hypotheses and the alternative hypotheses. I would like to give a little bit of an explanation in this recording. This is going to be a significant issue in the assignments, in the labs, as well as the quiz and midterm, final, whatever happens. So I wanted to make sure that with the example and explanations I'm going to provide, the concept is very clear. Let me share my screen with you. And we have discussed in the past that we have null hypotheses, H0, H0, versus the H1 or HA, A is standing for alternative. So H0 and H1, 0, 1, or H null and H alternative. Now, if you remember, we have reiterated the fact that there is a null hypothesis and there is an alternative hypothesis in a sense that it is supposed to be mutually exclusive to this one. This graph does not serve the best to basically make it very clear. But when we say mutually exclusive, we have a very specific criteria in mind in this case, in this exercise. If you remember when we said that a person holding driving license is either 18 years old or older, the mutually exclusive part of it would be a person who is younger than 18 years old, 17, 16, 15, 14, up to 1. They are on the opposite side of the spectrum, but one thing is very clear: the summation of the population of the null hypotheses and the alternative hypotheses is going to be equal to the total population. If I wanted to consider that fractionally, if I wanted to say that I have normalized the population of the, that is going to be the target in the null hypotheses divided by the total population, and population of the alternative hypotheses divided by the population, then I'm going to say when we add them together, it must be 1. Let's try this once again. First and foremost, they are opposite each other. Second, when you add them up, you get the total population, or if you have them normalized, and when you add them up, it becomes 1. Let's try this one more time. A person is innocent until proven guilty. What is the null hypothesis? A person is innocent. What is the alternative hypothesis? A person is guilty. So if you add anybody who is innocent plus anybody who is guilty, when you add them up, you get 8 billion people on the planet Earth. That's the population we have currently. So you see what I mean? First and foremost, they are opposite each other: innocent, guilty. Second, when you add them up, you must get the entire population. That's called mutually exclusive. Let's try this something on another example. I would like to try that on smoking and non-smoking. When we say smoking and non-smoking, let's say non-smoking is the null hypothesis. I didn't explain the second criteria of the null hypothesis yet. If non-smoking is the population of the null hypothesis, then the smoking is going to be the population of the alternative hypotheses. Add them up and you get 8 billion people. Let's try this one more time. You could potentially say a person is a graduate of a university bachelor degree. Okay? So Either a person is a graduate of a bachelor degree or the person is not a graduate of the bachelor degree. If you add them up, you get 8 billion people. This is a very important criteria. They are on the opposite side of the spectrum, and they are going to add up to the total population. In this case, I mentioned total population to be the human population, but by population we call solution space, which means the entire space that is going to encompass both the null hypotheses and the alternative hypotheses. I want to see if I have another question. For example, if we say that a person has 5 fingers. Now, a person has 5 fingers. We go around and we find the space, the population for those people who have 5 fingers. And then we go around and we find people who may have 4 fingers, who may have 6 fingers, who may have 3 fingers, who may have 7 fingers, and so on. They are on the other side of each other. And if you add them up, you get 8 billion people. In one of the examples, if you remember, we mentioned that, for example, if you take a look at the fork, and the fork has 4 tines, okay? A fork has 4 tines. Let's call this null hypotheses. The anti-null hypotheses, the alternative null hypotheses, the H1 or HA will be any fork that is going to have 3, 2, 1 time, or 5, 6, 7, 8, 9, 10 times. Obviously, we don't have a population of fork which have 5 times or 6 times. We could potentially have a fork which has 3 times. Whatever that is not the population of the null hypotheses becomes the population of the alternative hypotheses. When you add them up, the population of the entire fork, whatever fork exists on the planet Earth, that becomes the total population. So I need you to keep in mind, the first question you need to ask is, what is going to be mine? You need to base that. You could decide what your null hypothesis population is going to be, and then contrast that with the one that is going to have to be for the alternative hypotheses. So that was the first condition, mutually exclusive. The second thing you need to keep in mind in the study is that what it is that you are investigating in both populations. For example, I'm going to say smoking and non-smoking. So let me give you an example. When I say smoking and non-smoking, obviously I cover the entire population. Every human being on the planet Earth is going to be covered. There are those who are smoking and there are those who are non-smoking. They are opposite, on the opposite side of the spectrum. When I add them, I get the total population. But the fact that I'm looking for the weight, I'm looking for the weight of the null hypotheses. I'm also looking for the weight of the on the alternative hypotheses. Weight becomes the common angle of view. Weight becomes the perspective I'm looking for null hypotheses population and alternative hypotheses population. That's going to be weight. So what do I measure? I measure the weight. So if I take a look at the blue line, and in this case it says H0, H0. So the blue line indeed is the weight, because I need the 2 graphs to be of the same characteristics, attributes. I can't compare orange and an apple. Both of them have to be oranges. Both of them have to be apples. So when I take a look at this, both of them have to have amplitude reflecting the weight of the people in null hypotheses or alternative hypotheses. I could potentially go on and say that I want to have I want to see the smokers are going to be more prone to get cancer compared to the non-smoker. What is my population? A smoker, non-smokers. That's the population. What is the common angle I'm looking at? Cancer and cancer. And then I'm going to say yes or no, and accordingly make that kind of a relationship, and the study moves on. So I need you to realize that there must be a common attribute that you're looking. You could potentially say the mortality rate. The mortality rate. Okay, I'm going to claim that COVID-19 has increased the mortality rate. Okay, people who have COVID-19 infection are more likely to die than people who don't. Okay, that's a statement. First, what's my population? People who have COVID-19, anybody who doesn't have COVID-19. Okay, and together that becomes 8 billion people. That's the first thing. COVID-19, people who are infected with COVID-19 and people who are not infected with COVID-19. What am I looking at in these two populations? I'm looking at the mortality, the death rate. So the curve in both of these populations have to be the same attributes: death rate, dying, things like that. So you need to basically chew on this fact, how you're going to set it up. Now, there are times that H0 could exist, and H1 may not even have a population. For example, as we said in the past, if we say every driver is going to be 18 years old or older, then obviously that's the entire population of those who have driving license. But at the same time, if you take a look at people who are younger than 18 years old, the population is zero. There is no way government is going to allow you to do that. Let's try this one more time. I'm going to say that when you go and pick up a box of forks that are noted as 4 times in it, I'm going to say there is no way you are going to find a fork in that box that is going to have 3 times, right? So I'm trying to say that the manufacturer who is manufacturing the forks with the 4 time box is going to only include 4 time box, okay? So what is it that I'm trying to do? I'm trying to take a look at the forks with 4 times and forks with 3 times, 2 times, 1 time, 5 times, 6 times, 7 times, 8 times. Obviously, we don't have, as I said, anything more than 4. Doesn't make sense. We don't even have manufactured them anyway. But if you take a look at that, I said the box that is made primarily for fork that has 4 times. Obviously, if I put my mind right to it, and if the devices and the robots and the automation system that is going to basically process and make the forks with 4 times, obviously they are not supposed to make mistakes. And if they don't make a mistake, then the fork that is less than 4 times in that box, the box that has the sign of the 4 times, the fork is going to be empty. What does it mean? Any box that you open up that has said that the fork has 4 times, you open them up and you take a look at the fork. Is it 4 times? Yes. You put it on the side. Another one. Is it 4 times? Yes. You put it aside. Another one. Is it 4 times? Yes. You put it aside. Another one. Is it 4 times? No. It's 3. What happened? There was a process error. Something has gone wrong, and the machine that they're supposed to make 4 times didn't make it. That is when our red alert starts. You need to have this mentality very clear so that you can potentially succeed in the quiz and midterm and final and everything else. If this is supposed to be the chart for innocent people, then obviously, what's the idea? The idea that we would like to have, the idea is basically this. This is a normal distribution. We are happy with 95% confidence interval, 95% being in the middle of the system. So if I say 2.5% here and 2.5% here, 2.5 and 2.5, that will be 5, and everything in between is going to be 95%. We will say that the statement is correct is 95% of the time, it is correct. And we are happy with that kind of accuracy, with that kind of conclusion that we have. We talk about accuracy and everything else later, okay? So I need you to keep that in mind. I need you to keep that in mind, that if this population is going to be reflective of the innocent people, and I say this is 350 million people in US. Everybody, I don't want to use everybody, the word everybody. I want to see a person living in US is innocent. And then my concern would be, is that person guilty or not? Now, if the number of people in US who go to the court and become guilty is less than 2.5% in terms of probability, when you divide with the population size and everything else, 2.5% here and 2.5% here, then you are going to say, yes, the statement is correct, that a person living in US is innocent. You know what I mean? So this curve is primarily dedicated to innocency. And if it is primarily dedicated to innocency, this area will be the people who are going to be found guilty by the court of law. Okay? Now, if this is more than 2.5 on this side and this side, eventually more than the combined part is going to be more than 5%, then I have a red alert. 5%, 10% of the people are guilty, found guilty in, and there are countries on the planet Earth, by the way, that if you go to court, they will find you guilty anyway, right? So if 10% of the population is guilty, something must be wrong. The population is not innocent. And that is a statement that we have said that is readily you go and you pick up anybody on the street and that person is going to be innocent, that statement is no longer going to hold true. So this is very important. And the question I'm asking and the topic I'm asking you to focus is this. What is this curve? And what is this in relation to that curve? Okay, let's go back to my case here. This is for null hypotheses. This is for the innocency of the population. Then I'm going to have a population when I have suspicions, I have evidences, I have documents, I want to pick up people to go to the court, and I'm going to assume this population you see is going to be guilty. I want to go to extreme, and let's say, again, this is I don't necessarily believe in that statement, but I want to make it. Let's go to a prison. I'm going to say you go to a prison, and the prison, obviously everybody is supposed to be guilty. Otherwise, why they are in prison anyway? And then there are people whose evidences are going to be re-examined. And after re-examination of the people who were in the prison, we realized that the people who were in prison obviously were found guilty on a wrong document, on a wrong testimony, on a wrong procedure. They were indeed innocent. So once again, I'm asking you to take a look at in your mindset that what is the curve representing and what are you trying to find in that relation? If I find this color is in relationship to innocency. If this is guilty, in relationship to innocency. If this is innocent, in relationship to being guilty. Now imagine if I go to the prison and if I do, and the idea is this, anybody who is in the prison, sorry, I don't want to use anybody. A person who is in a prison is guilty. So that's my statement. So you're going to take a look at this as the person who is in prison. But then I'm going to challenge you. I'm going to say the system has failed partially, and I'm going to show you that more than 5%, if it is left tail or right tail, 5%, or 2.5 and 2.5, if it is two tails, I'm going to show you that more than 5% accumulative are going to be innocent. And that's going to be a red alert. That's going to be a red alert for the justice system. How did you get these people in the prison in the first place? You are not finding the guilty in the right way. You made an error. So I want to explain what these relationships are. So please remember, there are two of them, and you need to keep that in mind. So this is what I mean. So the person is innocent, but then you find them guilty. This is type 1 error. So this is type 1 error, this one. This is type 1 error in relationship with the innocency of the population. And then we have people who are basically who are guilty, and then basically we may have found them innocent or some type of mistakes we have done. So this yellow one is going to be type 2 error. So all the time you need to be conscious about exactly what curve it is and what are you looking for. And here is the endpoint. The endpoint is, if you can, for example, when I say a person is innocent until proven guilty, you really don't want to go after this curve. This curve has been proven for centuries, thousands of years. And therefore, this curve, you don't even establish it. You basically go into the prison system and you see whether you can actually challenge that. You see what I mean? When I say a fork has 4 tines, there is no the alternative hypothesis is going to be extremely small, maybe even non-existent, because you let it go with the rule of the mechanics and robots and automation system. There is no way they are going to make mistakes. This population is going to be extremely small, if it even exists. So what do you do when you are dealing with fork, with 4 tines? You are going to open up boxes of 4 tines and look for tines that are not, for forks that don't have 4 tines. So this is about boxes of 4 tines, and you're looking for forks that are 3 tines, 2 tines, 1 tine, 5 tines, 6 tines, 7 tines. So you want to basically, so this is your examination. The examination says you cannot easily establish the alternative hypotheses because its population is extremely small, okay? So if it is small, still you have a chance to reject the null hypotheses, and the only way you can do it is to open up all of the boxes that exist and then take a look at the fork and see whether they have 4 tines or not. And if they don't, and you say 3 and 2 and 5 and 6, and this is going to be slicing toward inside my confidence interval, then I'm going to begin to doubt my statement that forks in this type of boxes have 4 tines only. We found a mistake with the machine and robot, and they need to go on back and fix it, okay? Now, but there are other cases, and this is what most of the time happens. You don't have a precedence. Let me give you another type of a precedence. For example, a vaccine is going to save lives, which means the mortality of the people who got vaccine or vaccinated is going to be less than those people who didn't get vaccinated. So what the idea is, for example, COVID-19. Let's not even mention COVID-19, measles or something before, doesn't matter, anything that you can. So there is a specific illness, and that illness, there are people who take vaccine and there are people who don't take vaccine. So you see how I'm going to formulate my population. You need to formulate the population of the null hypotheses and anti-null hypotheses, which is alternative hypotheses, right? So I'm going to look at the people who got measles, and then I'm going to have from that set, I'm going to have 2 populations in mind. I'm going to have the people who are vaccinated, and there are people who are not vaccinated. So if you take a look at that, I mean, traditionally, before the vaccine for measles has been discovered, I would say that vaccination in general is going to save lives. And that has been established, basically, precedence, right? But in this case, just the vaccination for measles just was discovered yesterday for the sake of my example. We do not know the efficacy of the vaccine that has been produced. And what we are going to do, we are going to actually go through the population. This time, I do have 2 populations. Null hypotheses, the population for null hypotheses, and the population for alternative hypotheses. Do you see what I mean? And I create that. I go and pick up 2 sets of people, of course, with all the scientific conditions and questionnaires and background check and everything else is done. And I'm going to apply the vaccine on one group and I'm going to apply, and I'm not going to apply vaccine on another group, and I'm going to take a look at the outcome maybe after 6 months, after 1 year, to see what is the mortality rate of these two sets. You see what I mean? Now, you could potentially pick up any of these two sets as your null hypotheses. It depends on what you want to disprove. So I'm going to disprove, for example, the people who got who do not get vaccinated are as safe or perhaps in better shape compared to the people who are going to get vaccinated. Call me a skeptic. I'm going to say if you take vaccination, you are going to die sooner than I am. Okay, so that's what I'm going to say. Make sense? So I'm going to say if you don't take vaccination, you live longer. And again, this experiment is not easy. It is very complex. It has so many parameters, youth, existing conditions, everything. But at this time, that's beyond our point. The idea is I want to disprove that if you don't take vaccinated, you'll live longer. In order for me to do, you don't die as many. In order to disprove that, I'm going to go into the set of people who are going to be vaccinated. And I'm going to take a look at the mortality rate. So let's say that this is people who didn't get vaccination, and this is the people who got vaccination. Now the mortality rate, this is the curve for mortality rate for people who got vaccination, and this is the curve for mortality rate for people who didn't get vaccination. Again, the complexity aside. Then I'm going to take a look at the mortality rate, and what I'm going, and this is going to be the people who are going to perhaps die. And then what I'm going to say, I see the yellow is actually going to get further into my 95% confidence interval. It's going to eat a slice of my 95% confidence interval. If I see that the people who took the vaccination and the mortality rate is actually eating up the slice of my confidence interval, then I'm going to say I failed to reject the null hypothesis, which was if you don't get vaccinated, you live, your mortality rate is going to be lower. So that was the null hypothesis. You can arrange it either way. You need to choose the null hypothesis and then attack the anti-null hypothesis and study the anti-null hypothesis. So you're going to do that, and you're going to take a look, and you see, no. As a matter of fact, people who took vaccination, apparently the mortality rate was even less than 0.025, 0.05. It was 0.01. And therefore, you are going to reject the null hypothesis. The claim that if you take the vaccination, of course, this one, they say if you don't take vaccination, the mortality rate is going to be basically lower. So obviously, at this time, I prove to you that if I take vaccination, my chance of dying because of the illness that is common, and by the way, in the two population, is obviously the chance of dying is going to be less and less and less. And that's going to be a proof that the vaccination is working. You need to find the opposing parts of the spectrum, and you need to see what you are looking for. That's the amplitude of the curve. That's the amplitude of the curve. And then you need to see what is this versus this, and so on. You need to basically make sure that you understand the entire process. Now, in that normal curve, we said the p-value, and for example, if we say 0.05, then it's going to be 0.025, 0.025. We spoke of that before. We already have 95 confidence interval, and that's going to be this one. And then we have, this is again another figure that is reiterating that part. We also said that when you go to the actual experiment, because your experiment is not necessarily continuous. For example, the number of people who die and the number of people who don't die. I mean, it's just number. It's going to be a discrete number. And obviously, they are not going to be continuous. So there are continuous function and there is discrete function. So you need to be aware of that. And in discrete function, you can still do what we call the p-value calculation and then decide whether that is going to sustain or not. Now, in the following exercise, I'm going to talk to you about the quiz. And I'm also going to talk to you about a lab. Thank you, and I hope it is clear. If it is not clear, let me know. Thank you.